Okay, so it's the last recitation of the semester and some Brown in motion problems, which we will do. And yep. So first of all, actually before we start doing the problems, let's just briefly talk about Brown in motion. So it's a stochastic process, of course. Let's refer to it as B of t. And it has the following properties. So at 0, it's equal to 0. Then has independent increments. So s less than t. And it also has stationary increments. So Bs is equal in distribution to B of S for all t. And the distribution of B of t is normal, would mean 0, and I guess I'm referring now to the standard Brown in motion where there's no coefficient of variance. So it's normal 0t, and it's also continuous. B of t is continuous, but that's sort of peripheral. Okay, so we'll be using these properties pretty consistently throughout the homework. You know what? I guess the book sort of defines the general Brown motion, not the standard one. So let's say that the variance is sigma squared times t. Now when sigma squared is equal to 1, we have a standard Brown motion. And this is independent increments. Independent increments and stationary increments. Okay. So now let's do the first problem, where we're asked to determine what is the distribution of Bt plus Bs. What is it? Yeah, Bs plus Bt. So where S is less than or equal to T. Now we know that taken by themselves, these are normal random variables, but now these are dependent, of course, because Bt is greater than S, so they're dependent, so we have to be a little careful. So, but we can rewrite this in a better way that will exploit the properties that we just mentioned over there. So we can say that this is just equal to Bs plus Bt minus Bs plus Bs. So this might seem a little silly in the beginning, but you'll see why this is important. And then we can sort of take the 1 Bs out of the parentheses and get the following expression here. Now, why did we do this? Well, it is because now Bs and Bt minus Bs are independent by the independent increments assumption. So, and we know that this is normal 0, and now let's assume that sigma squared is equal to 1. So this is normal 0s, and this is normal 0 t minus s by the stationary increments assumption. So we have basically a linear combination of independent normal random variables. So we know that this means that bs plus bt will itself be normal. Will be normal. And that's just a sort of a general thing about normal random variables. If you take any linear combination of independent normals, you will get a normal with a certain mean and a certain variance. So now all that's left to show is, or to explore, is what the mean and the variance is. Well, obviously, the mean here will just be, expectation is additive, so this just becomes the sum of the two expectations. So this is just 0. And now the variance of bs plus bt is easier to calculate if we just substitute the other expression that we have. So it's the variance of 2bs plus bt minus bs. And now, since these random variables are independent, we know that the variance of independent random variables is just the sum of the individual variances. So this just becomes variance of 2 times bs plus the variance of bt minus bs. So this, we just take the 2 out of the variance, so it's 4 times the variance of bs, so it's 4 times s, plus the variance of bt minus bs, which we know is just t minus s. So we finally get a variance of 3s plus t. So now we've fully characterized what this random variable is. It's normal, so bs plus bt is normal with mean 0 and variance 3s plus t. So, any questions on this? Okay. Okay, now let's do problem 2. So in problem 2, we want to find the conditional distribution of Bs given that the value of random motion at 2 points. So we want to find what is the distribution of Bs given Bt1 is equal to A and Bt2 is equal to B. And of course, here we're assuming that S is between T1 and T2. So if we have this bounded motion, and we know that at time T1 it's at this level A, and at time T2 it's at this level B, and we want to just take a random time between T1 and T2. So we know it goes up here, then it can do a bunch of stuff, but eventually it will end up at level B here. We want to figure out what the distribution of the value of the bounded motion is between these 2 time points, T1 and T2. Well, now by stationary increments, we can do something that's a little trick. So imagine that we sort of subtract A from all this, from everything, in this time interval, we subtract a from the value of the boundary motion, and then we start it at time 0. So, in other words, time t1 now, consider that to be time 0. So we have a time window of length t1 minus t2, and now s minus t1 is somewhere inside here. And we know that at time t1 minus t2, our boundary motion will hit the level a minus b, no, b minus a, because that's how far up our boundary motion has gone. So now, and now let's do exactly let's copy exactly what's going on here. So think of this as sort of a carbon copy of itself here. Now, by the properties of boundary motion, by the stationary and independent increments, this process here and this process here will have the same distribution. Because all that we're doing essentially is that we're restarting at an earlier time, and of course taking it into account sort of the net effect of what's going on here. T2 is equal to b. This will have the same distribution as the value of the boundary motion at time s minus t1. Now, given that at time 0, boundary motion starts at 0, and at time t2, actually, this is bs minus t1 minus a. Given that at time 0, we start off at 0, and at time t2 minus t1, we've reached the point b minus a. And actually, plus a. Okay. So, and now we can go back to our book, and they've derived sort of what the distribution is for these conditional random variables. Equation 10.4. Yeah. So, as the book says, expected value of bs minus t1 given b of t2 minus t1 equals b minus a. So this, refer to equation 10.4. Then this just becomes whatever plays the role of s here. So this is s minus t1 divided by t2 minus t1 times b minus a. So this is the mean. And then the variance of Ooh, thanks. This becomes S minus T1, or T2 minus T1, times whatever T minus S is, so T2 minus T1 minus S plus T1. So our random variable, therefore, I hope people can see this. Okay, just barely. Thus, the random variable that we're interested in, Bs minus T1 plus A given, I mean, the B0 is equal to 0 is sort of assumed. So this will be equal in distribution to a normal random variable with mean A plus this guy. And variance, the same variance here. And that concludes this problem. So any questions? It's just an application of what's done in the book. Only now we're sort of starting the Brown motion at a later time and applying the same logic. Okay. Okay, so let's move on now. So problem 3, there's an answer to it, and it's also quite tedious, so I won't do it. Okay, so let's go to problem 5. So here we define Tx to be the first time when the Brownian motion hits a level x. So this is the first hitting time of a certain value x. And we want to find the probability that, make sure I get this right, t1 less than t minus 1, so less than t2. So we want to find this probability here. Okay, so now we can rewrite this as the probability of t2 being greater than t minus 1, given that we just sort of condition on one of the two events times this probability. Okay, so now let's see, what is the probability of t1 being less than t minus 1? Does anyone have a wild guess? Brownian motion with zero drift means that it's equally likely to go up and down. So just with a very simple symmetry argument, you can just say that This probability is 1/2, because the Barron motion is equally likely to go in whichever direction. So it's equally likely to first hit 1 or -1. Now, say that it does hit 1 before it hits -1. What is the probability that then it hits, let's actually rewrite this better. So what is the probability then that it hits -1 before it hits 2? So what's this probability? Well, again, and we're not really doing this very rigorously, because to do it rigorously you need to use martingales. But given that we first reached 1, so given that our Brownian motion now, so if we sort of look at it pictorially, so we reach 1 before we reach -1. So Brownian motion might do some things, but eventually it reaches 1 before it reaches -1. And then we want to calculate the probability of it reaching -1 before it reaches 2. Well, it turns out that, this is of course the same probability as the Brownian motion starting from 0 of reaching -2 before it reaches 1. And this probability, it becomes proportional to the length of the interval that we're trying to reach. So it ends up being, so -1, so it's actually 1/3. And the reason why this is so, it's because in general, let's just write this. So, and this can be proved rigorously, but in general, if we have 2 points, A and B, so for, I guess, A less than 0 and B greater than 0, the probability that TA is less than TB, this just becomes, you remember the formula, so it's B over B minus A. And similarly, it's just the absolute value of A, or minus A, over B minus A. So in our example here, the probability that we reach -1 before 2, this of course if we start at 0, okay? This is starting at 0. So if we start at 0, the probability that we reach -1 before we reach 2 would just be 2 over 3. And then, of course, probability that we so it makes sense, like, if B is very large, right? Yeah?
You said the probability of reaching -1 before reaching 2 is 2/3. Isn't it 1/3?
No, it's 2/3.
Reaching -1 first?
Well, think about it, right? -1 is closer to 0 than 2 is, right?
I thought you were talking about this.
No. This is in general. So this example sort of generally builds on that. But now the difference now is that we're not starting from 0, right? It's like we're starting from 1. So in general, this is what we have. And now, so the answer here would be just 1/2 times 1, or 1/3 times 1/2 equals 1 over 6. And this is for standard Brownian motion. Any questions? Okay. So let's do now problem 6. But before we do problem 6, we'll note about hitting times and so a very useful property of standard Brownian motion is that we have, if we say take a certain interval and we want to figure out what the probability is that the Brownian motion exceeds a certain level c, which is equivalent to saying what is the probability that the maximum over this interval is greater than c, then this probability is equal to, I mean, it's of course equal to the probability that the hitting time of c is less than t, right? And it turns out, if you look at your book, and by using the nice symmetrical properties of the Brownian motion, this just has this very simple representation. So it's 2 times the probability of b of t being greater than c. Well, actually, so this is a very nice and important property of the Brownian motion. And it's something that we'll use in the next few problems. So problem 6. Suppose you own a share of a stock whose price changes according to standard Brownian motion process. Suppose that you purchased the stock at price b plus c, and the present price is b. You have decided to sell either when it reaches b plus c, or when an additional time t goes by. What is the probability that you do not recover your purchase price? Okay, so we buy stock at level b plus c. Right now, the stock is at level B. Is at B, and we will sell if stock reaches level B plus C within t time units. And that's the only way that we will recover our investment. So the probability of recovering, so the probability of recovering the purchase price is just the probability that the maximum level, I mean, also we're assuming that the stock moves according to a Brownian motion. So it's like saying that we're interested in the probability of the maximum of the Brownian motion in this time window 0t exceeds a level, well, we're starting from level B, and we want to go up to B plus C. So we want to see, well, will the price move more than C? Because we're already starting from B, I'm assuming. Yeah. Yeah, because it's like we're saying probability of B plus the maximum is greater than B plus C, so the B's cancel. Okay, so then that means that the probability of not recovering, of incurring a loss, is 1 minus this probability. So, and given what we just talked about over there, we have a very nice expression for this. So it's 1 minus 2 times the probability of B of t being greater than C. And of course, B of t is normal 0t, so we know this probability. Okay. Any questions? All right. Okay, now problem 7. Problem 7, we want to calculate something that's a little more complicated. So now we're looking at time that is between t1 and t2, and we want to figure out if the maximum at this time exceeds a certain level c. So this is exactly the same thing as before, only now we don't know what the value of the Brownian motion at time t1 is. So we need to condition on it. So let's condition on the value of the Brownian motion at time t1, given that t1 is equal to y, and times the probability okay. So now it all becomes a matter of finding this probability here. Well, let's see. So okay. So again, we'll draw a little picture because I think pictures are helpful with Brownian motion. So we have time t1, time t2, and got this level c. So okay, so let's say that, so there are sort of two cases that can happen. First of all, let's say that the value of the Brownian motion at time t1 is at some level y, which is less than c. So Brownian motion does some stuff, and it goes up to there. And then we want to figure out what is the probability that in this time window t1, t2, we will hit level C. So, I mean, in any case, this, by the stationarity property of the bound motion, just becomes equal to the probability, the maximum now from 0 to t2 minus t1, because this is the length of the window that we're looking at, bs, greater than now the difference of c and y. But now we have two cases to consider, right? So let's assume first that y is strictly less than c, or is less than c. So it's this case here. Well, in this case, then this maximum is just the same thing. So but now, if y is greater than c, then this is the probability that the maximum of our Brownian motion is greater than some negative number. And what probability is that? It's just 1, right? Because the Brownian motion starts at 0. So we get that this integral here, just plug all this stuff back in and, well, we get something. I don't think you need to write this explicitly, but so when y is less than c, we get the probability that the max is greater than c minus y. So this is 2 times the probability of Brown motion at time t2 minus t1 is greater than c minus y times the density. So and then plus, now if we take y to be from c to infinity, this conditional probability just becomes 1, and we integrate here. So that's the answer. So any questions? No questions? Okay. So now, let's do sort of the last set of questions, which have to do with martingales. And it's too bad you don't do more of these. It's very useful. So the process y of t is a martingale if, well, there's some other conditions too, but for our purposes, if we have that the expected value of y of t given the value of the process at some point u, which is between 0 and s, is just equal to y of s for all s that are less than t. So in other words, given you know sort of if the present is time s and you know all the history of what's happened up to time s, and you want to project into the future what the value of the process is going to be, well, your best guess would be to just say, well, it's whatever I have now. So it's sort of the intuition behind it, and people have also looked at it in terms of fair games. So if given your current earnings, now if you want to figure out how much you might win in the future, well, you're likely to stay the same. That's sort of what this is saying. So now, there's a lot of gambling applications. So now we have a bunch of things that we can show. So problem 16 is to show that the martingale has a constant mean. And that's fairly easy to show, right? Because, well, let's take the expected value of y of t. Well, we can do a tower property here, because we know that these two expectations are equal, right? We're just conditioning on the value of w's of y0. And now, by the martingale property, we know that this is just equal to y0. So this is just expected value of y0. So this means that martingale has a constant mean at all times. So for any t, the mean at time t is equal to the mean at time 0. 17. We want to show that Brown motion is a martingale. So show that Bt is a martingale. And that's also pretty easy to show, because let's consider the expected value of Bt given the value of the Brownian motion at some point from u from 0 to s, where s is less than t. So s is less than t. Well, the way to sort of think about this is to do that trick that we did earlier. So rewrite b of t as b of t minus b of s plus bs, given now the same thing. Now let's break this into two expectations. So this is t minus bs, given all that stuff, plus the expected value of bs, given, I don't want to keep writing this thing. Okay, so one of the major important properties of Brownian motion is that it has independent increments, right? So by independent increments, we know that the value or the random variable bt minus bs is independent of anything that's happened before time s. So this conditional expectation is just equal to the unconditional expectation. And this is by independent increments. And now here, we want to find the expectation of bs given some information which contains Bs. So that's just Bs. Can people see? Yeah. So that's just Bs. And now we're done because, well, what is expected value of Bt minus Bs? It's 0 minus 0, so it's a big 0. And we're only left with B of S, which is exactly what we wanted to prove. So standard Brown motion is indeed a martingale, because this is 0. Any questions? Okay. Now let's do the two last problems. So the two last problems have to do with something that's called the optional sampling theorem, or optional stopping theorem. So basically, the optional stopping theorem this says, like, under suitable regularity conditions, which I think for our purposes will always be met, we can say that if t is a stopping time for a martingale y of t, then the expected value of the martingale now evaluated at this random time, which is just a stopping time. It's not time s or time t or time anything. This could be like the first time the process does so and so. Like if you're playing in the stock market, the first time the stock price goes to level A. That's not a deterministic time. It's a random time. But it is a stopping time because it's not clairvoyant. It doesn't see into the future. It only depends up to information that is available in the present. So the expected value of the martingale, evaluated now at this random time, is equal to the mean of the martingale. And t has to be a stopping time. So examples of stopping times would be the first time I get an 100 on my exam or something. But you can't say that the last time I get an 100 on the exam is a stopping time, because by saying that you're assuming that you know what the future is. So that's not a stopping time. Whereas for our purposes, wherever you see the first time that something happens, then that's a stopping time. So, see problem 20. So here we let t be the first time, so I guess minimum of t, such that the value of the Brownian motion is equal to 2 minus 4t. and we want to find the expected value of this time. Well, we remember that b of t is a martingale. So we can just now apply, and assuming that this stopping time works and meets whatever conditions are there, we can just apply optional stopping. So in other words, the expected value of b of t will just be equal to the expected value of the Brown motion at time 0, which we know is 0. So we get that 2 minus 4 times the expected value of t, because we know that at time t, Brown motion will be exactly equal to 2 minus 4t, right? And this will be equal to 0, which implies that expected value of t is equal to 1/2. Any questions? Okay. So let's do now problem 21, the last problem that we'll ever do. So here we have a Brown motion with drift and parameter sigma squared. So bt plus, no, sigma bt, there, plus mu t. And we're assuming that mu is positive. And now we define the stopping time t to be the minimum time such that x of t will hit a level x, and which of course is just equal to the minimum. If we rewrite this in terms of the Brownian motion, it's the minimum time that the Brownian motion hits a level bt is equal to x minus mu t over sigma. And we want to figure out what the expected value of t is. Well, it's again, we do the same thing. We apply optional stopping to the Brownian motion. And note that things are not always this simple. Like, there are a number of martingales that are associated with Brownian motion. A few of them are in your book, and sometimes, you have to sort of play around with the different martingales until you can get what you want. So, but in this case, this martingale is going to work because expected value again of b of big T is equal to 0, which means that x minus mu times expected value of t divided by sigma is equal to 0. So the sigma disappears, and we're left with that the expected value of t has to be equal to x over mu. And that's what we wanted to prove. So, any questions? Yeah.
Question 17 again.
17?
Yes.
This one, yes.
How do you get from the second step?
From this, how did I get from the second step?
Yes, the second step. Yes.
Okay, sure, yeah, this might not have been very clear. And to make it a little more clear, I'll be less lazy. Okay. So, okay, so the question is, how do we go from this step to this step? Well, so there are two expectations that we're calculating, right? The first one we claim is just this conditional expectation. We claim that it's just equal to the unconditional one. And why is that? Well, because if you look here, it's like we're taking the value of the Brownian motion that is now in between the interval s and t. And we know by the property of independent increments, the Brownian motion so we know in other words this thing here, that bt minus bs is independent of bs. And actually, maybe I should have written this a little better. It's independent of bu, where now u ranges from 0 to s. They're independent. So because they're independent, this conditioning has no meaning. So we just uncondition, and now we just take the expectation of bt minus bs. bt is normal with 0, mean 0. bs is normal, mean 0. So the whole thing will have mean 0. And then here, we're saying, okay, what's the expectation of bs given information that contains the value of bs? So whenever we have something like this, we just take it out of the expectation because we know what it is. Okay? So that's how we go from here to here.
In this case, would expectation of BS be 0?
No, because we're conditioning on information which contains what the value of bs is. This is like saying expected value of x given x. Well, that is just x. It's not expectation of x. See? So expected value of x given x is just x. It's random. It's not the expectation. Yeah, so I guess when I wrote down the properties of the Brownian motion in the very beginning of the recitation, I think I just wrote down bt minus bs is independent of bs. What I really meant to say is that it's independent of anything that's happened in a non-overlapping interval. So of all the prior history before time s, or at time s. So, any other questions? Okay, thanks.